Okay, it started. And yeah, so basically today we continue our course on advanced quantum computers, right? And today finally we will get to quantum mechanics, the basics of quantum mechanics. But before I go there, let me tell you a little bit more about linear algebra, basically the concepts that we will need. And the first concept that I want to tell you today is this concept of function space. Function space. Right, so function space. Apparently, this is a space of functions. And at this point, we will see like why basically we use this cat and bra notation. Basically, that's because this vector that we denoted by, for example, psi cat, right? This psi can be a vector of any kind, including a function. So basically, this can be some sort of a function, like this, like a function f of one variable x, or some function, maybe another f of coordinate r, etc. So this this bracket notation allows you to represent any vector, a vector of any kind, using basically the same notation, the same language. And when we talk about functions and two functions and vectors like this, of course we need to define the inner product of operation of two functions from this space, right? And in this case, the operation of taking the inner product is modified, and now for this function space, let me put f x first. So this is my first vector, right? Then my another vector. So this is vector function. And this inner product of two vector functions is equal to the integral of the first one, complex conjugated, right? So this f of x is the bra vector here. So it's supposed to be complex conjugated. Then gx dx. So this is the integral of one function. So basically, this is a convolution, right? The integral of a product of two functions, and of course, I mean, the result is also a constant, and this way, like for example, if you take your integral from minus infinity to plus infinity, you will get some constant, and in this sense, this operation is similar to what we used to in the vector space. And I guess the best way to grasp this idea, why we basically need this function space, is the following example. So let's consider a set of functions fn of x, and it's equal to 1 over square root of pi cosine nx, right? And another function gnx is equal to 1 over square root of pi sine of nx. So set of two functions, fn and gn. Right? So now let's calculate the inner product of any two functions from this set. So for example, I write this fn x, then gm. So n doesn't equal to m now. So by definition of the inner product of two functions, I write from minus pi to pi, because this is the periodicity of these functions. Cosine and sine are periodic with the period 2 pi, or from minus pi to pi. So it's sufficient to take this integral from minus pi to pi. And then 1 over square root of pi times 1 over square root of pi gives me 1 over pi. This is so-called normalization coefficient. And then cosine nx, I don't take the complex conjugation because cosine is real valid function now. And sine mx. And what? And dx, of course. And dx. So we know that the integrals like this is equal to 0, basically, when the n doesn't equal to m. So when n doesn't equal to m. So for different n and m, these integrals always give you 0. So in this sense, these functions fn and gm, they are orthogonal because their inner product is 0, right? And the same way, we can write that f of n x gm x, assuming that n can be equal to m now. So this integral from minus pi to pi, 1 over pi sine nx sine mx dx is equal to 0, as we just discussed, when n doesn't equal to m, and 1 when n equals to m. That's why we have this normalization coefficient 1 over pi. So the integral of cosine nx times sine nx gives you 1 over square root of 1 over pi, and then you basically divide both parts by pi, and you get this 1 here. So these functions fn and gm are orthogonal and orthonormal because their inner product is 1 for the same n, for the same n and m. And so let me see. So we denoted by g sine and f cosine. Okay, and the same way, the product of two functions f is also 0 when n doesn't equal to m, and 1 when n equals to m. And by the way, we denote this by the delta Kronecker, right? nm. So delta Kronecker is the identity matrix. Basically, when n equals m, delta Kronecker equals 1, and when n and m different, this corresponding component of the delta matrix is 0, and this gn of x times gm of x also the delta nm. So you're supposed, I mean, you probably are aware of this result, and if you, I mean, you can take this integral and check that. I mean, this result. The main point here is that we can use these functions f and g now, these basically sine and cosine functions, to represent any function, or better say any vector function from this vector linear vector space. So let's write it down here. So we can introduce a vector function space with basis fn gn, right, for different n and m, and we can represent any vector. Let's quote it, because this is actually not a vector but function. In this space, as a series, as a typical series that we have for any vector representation by vector components. Let's say a function a of x, right? It is equal to the sum with some coefficients n, an, vectors f n x plus bn gn x. So if you, I mean, now you can guess that this is actually nothing but Fourier transform, right? So this is the formula for Fourier transform. Fourier transformation. Fourier transformation formula. And taking the product so basically taking the product of this Fourier transform, for example, by okay. For example, by fm of x bra on the left, right, what I get the following: fmx, then ax ket equals to the sum an, then fmx fnx plus basically bn fmx gnx. So we see that this guy is equal to 0 because any product of f and g equal to 0, and this one is equal to delta function or delta Kronecker mn, yes, and the sum of so now we have what we have, this sum an delta mn, and it's equal to a with index m, right? Because any delta element, I mean elements of this delta Kronecker equal to 0, except for the case when m equals to n. So from here I conclude that am, one of these elements, is equal to the inner product of my basis function fmx on ax, right? So this is nothing but the projection of a function ax on the vector fmx. In the same way, I can obtain another formula for bm, right? It will be gmx ax, like this. So again, this is nothing but the projection of vector ax on the corresponding eigen corresponding vector gm. So how it looks like, or how you can like imagine all this. So let's suppose you have this vector space, and then you introduce a set of orthonormal vectors, right? So these are orthonormal vectors. For example, this is f1x vector. This is g1x vector. This is f2x vector. This is g2x vector, and etc. Etc. Let's denote this, for example, fnx vector, and this is gnx vector, right? So you introduce this space, and I mean, I draw this picture on the plane. That's why, I mean, I cannot represent these vectors are orthogonal, because for example, in this case of Fourier transform, how many dimensions we have? We have infinite number of dimensions, right? This is the infinite space, because to represent any function as a Fourier transform, we need an infinite number of sines and cosines with different basically with different frequency. And of course, I mean, this is something that you probably know from the signal information theory, that at some point, of course, we can truncate this space, because we never work with infinite series. So we truncate at some point when we have this representation of a function like with a good accuracy. But theoretically, in general, this space is infinite, right? And then we have a vector function. This is our ax here. And then we find the projections of this vector function on the corresponding vectors, right? And this is nothing but these coefficients a, n, b, n, and etc. for all other projections. Very good. So this is about the vector function space, and why we use this cat-Brown notation and why it's so convenient for us. So, and now at this point, we can introduce the concept of Hilbert space. Hilbert space. So this is an important concept because all our quantum mechanics, quantum information theory, everything basically happens in this Hilbert space. So we introduce this Hilbert space as a, I mean, there is a like very rigorous mathematical definition of Hilbert space, but for our purpose, it is sufficient to say that Hilbert space is a complex function space, is a complex function space with by the way, this space can be of infinite dimensions, can be infinite dimensions with a basis with some basis, let's denote it by psi n. Right. So the keywords here are complex. This is complex space. This space can be of any dimension, including infinity. And yeah, so in this space we introduce this basis of functions, and yeah, and in this space we can represent any function, like any state that belongs to this space, as a series like this, Cn times Cn. Right. So this this Cn are basis functions, basis vectors. It would be better to say basis vectors, and Cn are complex coefficients. The fact that this space, this Hilbert space, is complex, it basically means that the projections of this vector psi on the corresponding basis vector psi n is complex. So projections are complex. And this is very important for the quantum theory because, as we will see, this Cn correspond to the probability amplitudes, and they must be complex. Very good. So now at this point, again, I can multiply this expression by, let's say, psi m on the left, and what I get, I will get Cm is equal to psi m psi, right? The way as we did where we did here, and at the previous lecture. So this is how, basically, the way how we obtain this complex coefficients. Complex coefficients. So they are projections of vector psi on the basis vectors. Okay, and and now we already know that this psi and psi m can be actually vectors, right? Vector functions. And if we deal with vector functions, I can write the same. This is the inner product. So if this psi m and psi are functions, then the inner product of these two functions will be psi m complex conjugation, because this psi m is bra in this expression, and then psi, well, let's write this x psi x dx. So this is basically the same. We use this formula one here. For example, when we work with like discrete spectrum, when, for example, this Cm can be represented as a matrix or basically vector, and we use this formula too in the case when Cm is actually a function or continuous spectrum. It gets continuous spectrum. So we will discuss that as well today. So as I said, the Hilbert space can be of infinite dimensions, but of course it's not convenient to work with space like this. And for our quantum applications, like quantum information applications, we usually truncate this space to two-dimensional Hilbert space. So let's talk about 2D Hilbert space. 2D Hilbert space. And at this point, we can say that this is actually the qubit. Two-dimensional Hilbert space. So let's actually write this down. We truncate the Hilbert space to dimension 2, right? To dimension 2. So in the two-dimensional Hilbert space, we can basically any vector in this space gets two components. For example, vector A gets component A1, A2, and the corresponding bra vector is the Hermitian conjugation of the ket vector, right? And it will be the string of components B1 complex conjugation, B2 complex conjugated. So this is my ket and bra vectors in this two-dimensional Hilbert space. So accordingly, the inner product of B and A will be what? It will be B1 complex conjugated A1 plus B2 complex conjugated A2. And this is real. This is real number. And for example, the inner product of a vector by itself is the absolute value of A, right? And this is also a real number. Again, so this is the inner product. Let's denote this one. It's two outer products. Outer product is the, as we discussed, this is operator. So for example, A, B, it is equal to the matrix 2 by 2 with components A1, B1 complex conjugation, A1, B2 complex conjugated, A2B1 complex conjugated, A2B2 complex conjugated. So this is operator, and in the matrix representation, this matrix is represented by by these components. Basically, the the products of all components of the vectors with complex conjugation for the components of the bra vector. So and when we describe any vector in this two-dimensional Hilbert space, we of course can we have to introduce a basis. And as we discussed already last week, there are like many ways we can introduce the basis, because any linear space gets the infinite number of orthogonal vectors. So basically, you pick one vector, and then you can always find another orthogonal vector to the first one, and then you basically select these two vectors, and this is of course a basis. You can use this to represent a vector in this space, but then you can simply rotate this basis somehow, and by some angle, and it will be another basis. This will be another couple of two vectors in this space, and you still can use these vectors to represent any other vector in this space. So for the following, the basis vectors of like great importance are the following. So the first one, we denoted it by zero vector, and this is vector 1, 0, like this, and vector 1. This is vector 0, 1. So at this point, it's important to mention that this 0 and 1, we will see that they correspond to the this 0 and 1, they correspond to the, for example, to the state to which the quantum system excited, or it represents the orientation of a spin in space, etc. And we can say that, for example, if this number here 0 corresponds to the let me draw this picture here. So for example, this is the state 0 and this is the state 1. So this state 0 is the ground state, is the state of lowest energy, for example. And the fact that my excitation is in the 0 state, that means that I occupy the first state, right? So my ground state corresponds to my unit here in this vector at the first place in this vector. And then the second excitation, this vector 1, gives me 1 here, right? And if I would write something like the vector 2, for example, it would be something like this, 0, 0, 1. So basically the excitation at the third place, at the third state. But our space is two-dimensional, so you can remember that this index here corresponds to the place of this unit, either in the first place or in the second place. Anyway, so let's let's confirm that this is orthonormal basis. To do so, we take this product of 0 by itself first, right? So it will be 1, 0 vector times 1, 0 vector. So by components, y1 by 1 gives me 1, and 0 by 0 gives me 0. So the answer is 1. So these vectors are orthogonal. And the same way, 1 by 1 gives me 1, 0, 1, and 0, 1 column. So it also gives me 1. Right. Next, the inner product of 0 and 1 gives me 1, 0 here and 0, 1 here, which is 0, because 1 times 0 plus 0 times 1. And the same way, 1 times 0 is also 0. So this is the orthonormal basis. So this basis is orthonormal. And this is fundamental basis. Of course, we can introduce many other bases, and we will introduce some of them in a while. But this is kind of fundamental one, fundamental basis in the two-dimensional Hilbert space. So now let's consider a vector that is composed of these two basis vectors. Or in other words, I can say that now I consider the vector that represents the superposition of two basis vectors. Superposition of the basis vectors. Superposition. So I write this another psi vector, which is superposition of 0 plus 1. Right? So I can consider a vector like this, a simple superposition of two basis vectors. And this vector also belongs to this two-dimensional Hilbert space. So now I check that this vector is orthogonal. So I write this bracket inner product and get what? I get my 0 plus 1 times 0 plus 1. What I get? I get 0, 0 vector plus 0, 1 vector plus 1, 0 vector plus 1, 1. Not vector, the terms, the components. So recalling this result here, right, that this vector is orthonormal. So I conclude that these guys here, these terms equal to 0, and these two equal to 1 here and 1 here. So my answer is 2. So this vector of superposition of two basis vectors, it is orthogonal but not normalized. So I have to normalize this vector, and the way I do that, I simply divide this psi vector by 1 over square root of 2 and my superposition. Right, so this is simple superposition of two basis vectors. Excuse me, what was that, William? Okay. Very good. And yeah, let's write also this vector that we just obtained in components. So my prefactor is 1 over square root of 2, and this vector 0 is 1, 0, right? Plus this vector 1 is 0, 1, right? So how I sum two vectors? I simply sum the components. So it will be 1, 1, here, here. So the answer is simply 1 over square root of 2, 1 over square root of 2. So this is my vector of superposition. So any vector in two-dimensional Hilbert space is has two components. Accordingly, any operator in this two-dimensional space is 2 by 2. So any operator, let's say any matrix is 2 by 2 matrix. And so any operator can be represented by a matrix, and in this two-dimensional Hilbert space, any matrix is 2 by 2 because they act on a vector with two components. Right? And of very the most important matrices in this two-dimensional space are so-called Pauli matrices. Pauli matrices. So usually we denote them by sigma 1. You can meet like another notation like sigma x, or sometimes we also put just x here, something like this. So this is basically the same matrix, and the matrix itself is 0, 1, 1, 0. So the second one, sigma 2 or sigma y, you will see why we have this index x, y, and also z from the following, and also y matrix. And this is a matrix like this. So this is 0, I, 0. So another one, the third one, sigma 3, which is the same as sigma z, which is the same as z operator or matrix. And this is simply 1, 0, 0, minus 1. Right? And so these are three Pauli matrices. And we also add this identity matrix here, right? So this identity matrix, sometimes we denote this by I. You can also denote it by E, something like this. So this is nothing but the identity, two-dimensional identity matrix, 2 by 2. Okay. So why these matrices are so important? Well, there is a theorem that says that you can represent any operator in the two-dimensional Hilbert space using only these four matrices, the identity plus three Pauli matrices. So any operator in this two-dimensional Hilbert space is represented using this operator. We can actually write this down. Any operator in 2D Hilbert space can be represented via the Pauli matrices, plus identity matrix. Another point why these operators are important, because these matrices, Pauli matrices, they correspond to the spin state, right? This or the operation of measurement of a spin of a particle, like an electron with spin 1/2, or the same matrices correspond to the operation of measurement, the polarization of a photon, and etc. So these matrices are like very important for the following. And in fact, the way why I put this X, Y, and Z notations here is that the quantum computer people use these matrices as the quantum gates. So basically these three matrices, these are quantum gates that we will use extensively in what follows. Oops, I did something wrong. Oh. No, go back. Sorry. Yeah, so X, Y, and Z Pauli matrices, or in quantum information theory, they correspond to X, Y, and Z quantum gates. Several properties of these matrices. So first of all, X squared, is equal to Y squared equal to Z squared, and it's equal to identity matrix. So you can see this from the definition. For example, for X, you take the product of two 0, 1, 1, 0, and another 0, 1, 1, 0. And now when you take the product of these two matrices, you will get 1 here, 0 here, 0 here, 1 here. So this identity matrix. Why it's important? Well, because this means that these X, Y, and Z operators are unitary, right? Another property is that the determinant of these matrices, let's denote them by sigma. So let me put sigma 1 here, sigma 2, and sigma 3. So determinant of sigma matrices, the Pauli matrices, are equal to -1. Also easily seen from their definition. And another property is that the trace of all these matrices equal to 0. Again, very easily seen. For example, this z1 plus minus 1 gives you 0. Okay, and and so as I said, any operator in this two-dimensional space can be represented like this, right? And now we can recall this outer product notation to represent this operator. This A B operator is equal to what? Simply A1 B1 complex conjugated 0 0 state plus A1 B2 complex conjugated 0 1 state plus A2 B1 complex conjugated 1 0 state and plus A2 B2 complex conjugated 1 1 state. This is the representation of this operator, and this is the representation of this operator in the 0 1 basis. 0 1 basis. All right, so this is basically it about the linear algebra. Maybe maybe just a couple of two notes before we get to the quantum mechanics. So let me make two asides about operators before we proceed. So the first one, so we say that when we introduce a basis in a vector space, then we can transform this basis to another one, right? And of course, the operators also transform from this transformation. And so let's ask the question: how the transformation of how to transform an operator or a matrix from one basis to another, from one basis to another basis. So this is something called similarity transformation. In linear algebra, it's called similarity transformation. Similarity transformation. So how we do so? So we know that we have a, like, for example, we have an operator L hat, and we can represent this operator in a matrix notation like this, right? So this operator n n m. For example, in our two-dimensional space, it will be what? It will be a matrix with components 0, L0, then 0, L1, then 1, L0, and finally 1, L1. So this is this will be matrix like this. So and now we do this transformation of vectors n and m to another basis. So accordingly, our vectors, these basis vectors, will be transformed to another n prime, and another m prime. So how we do this transformation? We do this transformation through the unitary matrix or unitary operator, right? So I can write m prime is equal to my unitary operator u times old vector m, and this vector n also is transformed using this through this unitary operator u, right? So we have first we have our initial basis n m, and then we apply this unitary operator to transform this basis to another vectors m prime n prime. and let's say that also, for example, for this vector n prime, the corresponding bra vector n prime is equal to what? Is equal to the operation of this u n dagger, right? So I take the dagger of the matrix and vector, and this gives me the bra vector. And according to the properties that we discussed maybe 2 weeks ago, I can write it here, for example. If I have one vector or matrix, another vector or matrix, and take the Hermitian conjugation, it's equal to B dagger A dagger, right? So basically the same matrices, but written in the opposite order. So it's equal to what? It's equal to n bra times u vector dagger. Okay, so now let's write this new operator matrix for a new operator. It is n prime, then my operator L in another, in the new basis, and vector M also in the new basis. And it's equal to what? So I basically plug in this formula here, this one, and this one, plug into this formula, to this expression, and what I get n in the old basis, then u dagger, then my L in the new basis, then u operator, and vector m. So from here, I conclude that in order to make these matrix elements to be the same, basically unchanged, after the change of the basis, I have to change my my matrix this way, right? So it will be let me see. It must be my operator. It's equal to operator in the old basis is equal to my unitary operator u dagger, then L in the u basis, and unitary operator. And of course, since this operation, like changing of the basis, is like I can change this operation from one basis to another or back. I basically can simply write the same expression for the opposite transformation. So it will be also something like this. So this formula is fair for any transformation of a matrix or an operator when we transform the basis. And this is similarity transformation. Similarity to transformation. Similarity transformation. Very good. So let's write this down. So we transform a matrix. We transform a matrix or an operator. An operator by applying the unitary operator. By applying the unitary operator U. Basically from left and right. From left and right. From left and right, but when we apply from the left, we take the Hermitian conjugation of this operator. In the linear algebra, in the real space, this is something like, I mean, it's usually written in another form, like like this. Oops. So it's an inversion matrix here, then my operator, and then another unitary operator. Because in the linear space, we don't have these complex variables, complex matrices, and the Hermitian conjugation corresponds to the inversion operation to a matrix. But since we are dealing with the complex Hermitian space, we have to take into account that these matrices are complex, and we have to take the Hermitian conjugation of the unitary operator. Very good. So this was the first one, the first aside, and the second one. The second one. So operator in the matrix representation. The matrix representation, when the bases are the bases are functions, right? So we discussed that these Bryan-Cat notations, they include this option that these vectors are functions. So what if these vectors are functions? How we write the matrix in this function vector space? So we know that this vector or this operator can be, I mean, I repeat these words once and once again. That's just because to like you used to all this. So I can represent my operator as a matrix, like like this, right? To 1, to 2, etc., all the way down to L(n)(1), Ln(2), etc. So this is a matrix that represents this operator, and I can write this down like this: n, then L, and vector m, right? So this is what we discussed, for example, here. This is the way I represent my operator in a operator notation, in the matrix notation, and in this short form a representation of the matrix notation. But what about what about the situation when these functions n and m are functions? So these vectors are functions. So in this case, as we discussed today, the inner product of these functions is the integral of let's say some f n complex conjugation, the variable x, argument x, and then f m x dx. Right, this is the inner product of two vector functions. Vector product, inner product of two vector functions. Then the same way, like similarly, I can write these matrix elements n, l, m, these matrix elements that represent my operator L, right, in this form. So it also will be an integral. Then first this function, this bra function, which is fn complex conjugation of x, then my operator L, and then this last function fm x dx. All right, so this is the basically the representation of a operator in a vector basis when the basis is constructed of the vector functions. When this is not just vector like 0 and 1, but a function. In quantum mechanics, this is, for example, we meet this situation, for example, when we discuss a particle traveling in space, interacting with another particle and something, because these n and m are psi functions or state functions of this particle, and they are functions of coordinate in space. So that's why we have to take this integral. And accordingly, I can write, for example, for the Hermitian conjugation. Let's write this for the Hermitian conjugation. So let's take the Hermitian conjugation of this of this matrix element n, l, m. So let's take the Hermitian conjugation, this dagger. So what I do, I transpose my matrix, right? So now this element m goes to the first place, this n goes to the last one, as you probably remember, and this operator gets this dagger here, right? So I Hermitian conjugate this operator L, and transpose this matrix elements. And in this case, this integral will be what? It will be Fm complex conjugation x, then L dagger, and Fn x dx. All right, so this is basically all about the linear algebra, and this is everything that we will need for the rest of the course. So now let's start the second chapter. Right, so let's denote this. So let's say the first one, this linear algebra, was the first chapter, and now I can say this. We start the second chapter. Oops. Okay. Chapter 2. Basics of quantum mechanics. Basics of quantum mechanics. And the first subchapter, chapter 2.1. Let's call this the postulates of quantum mechanics. Postulates of quantum mechanics. So basically, I mean, we can discuss a lot about the history, how this quantum mechanics was established, and about all those concepts, etc. I think the best way for our course is to basically give you this information in a form of several postulates and basically discuss each of them a little. So the first postulate 1. Postulate 1. Let's name this a postulate of a quantum state, which basically says that a quantum state of any quantum system, a quantum state of a quantum system is represented by a vector. Represented by a vector where vector in a complex Hilbert space, in a complex Hilbert space. And since this is a linear vector space, at this point we also can say that the superposition principle holds, right? Because it basically holds for any linear vector space. So let's also write this down here. The superposition principle holds in this complex Hilbert space. So a quantum state of any quantum system is represented by a vector in a complex Hilbert space. So please don't ask me like what this vector basically, what is this base, what is this vector state? The answer is that like we still don't know. So what basically people who work in quantum area, what they basically say. So a quantum system of any kind is attributed by some psi vector state, psi vector state. And my way to introduce this is to say that this is just the way how we describe a quantum system. We don't know how a quantum system really looks like, right? We don't know how it really organized down there at the quantum level. The only like the best we can do is to describe, like introduce the theory that describes the behavior of a quantum system, and this theory is called quantum mechanics. And yeah, so this is basically the best what we can do. And we can judge upon like whether the theory is correct or not based on the conclusions that we derive from this theory, right? We calculate some like answers and some numbers, and then we go to the lab, do the experiment, and check if the theory works or not. So the point is that quantum mechanics and its more developed version called quantum electrodynamics is the most developed theory existing today. So it gives you some answers to some problems with overwhelming accuracy, the best accuracy that you can like get from a physical theory. But at the same time, quantum mechanics is all based on this concept of vectors, state vector, this psi state vector, and we don't know what it is. So this is basically the way how we describe quantum system. And also at this point, I have to mention that usually when people hear about quantum systems, they imagine something very small, like something nano or even at the level of elementary particles. So, well, this is not the case. So apparently the quantum mechanics manifests itself most at the scale of the elementary particles, but at some certain conditions, we can actually save or preserve this quantumness up to the macro scale. And in fact, in the vast majority of today's quantum computers, we actually use this quantum state of the macro system. not like elementary particle or something. We work with macro systems, and these macro systems, in some certain conditions, they preserve this quantum state for some time. And yeah, so quantum is not only about smallness, it's also about how we design our system to preserve this quantumness. Okay, so let's consider two examples. Example one. So as an example one, let's consider a particle like electron passing through a slit. Passing through a slit. Right, so this is the famous picture and experiment. So I assume that I have a slit in a screen, and this slit is like very small, and then I have a like electron, one single electron that comes to my screen, and and as we just said, I represent the state of this electron using this psi vector state. Psi vector state. And what I get after this screen? Well, the experiment says that I get a number of waves like this with different k vectors, k vector 1 that directs to this direction, k vector 2 that directs to another direction, k vector 3 to another direction, etc., and so on and so forth. So how it looks in the experiment? In an experiment, you send one single electron, and this electron, after the slit, can go to any of these directions. And of course, the electron itself goes only to one of these directions. But before you made your measurement, before you detect your electron, for example, going to this second path, you have to assume that your electron goes to all possible directions simultaneously. Then you send another electron, and again, this second electron also goes to all these directions simultaneously. But if you make the measurement of this electron, you, for example, can find this electron in the state 3, for example. The first one was in the second state, the third in the third state, another electron in the first state, etc. So you cannot predict with 100% confidence that you will find your electron in either state 1 or state 2 or state 3. You always talk about the probability of finding an electron in each of these possible states, probabilities. Well, so why I bring this picture? Because it nicely represents the idea of the superposition principle. So what we had before this screen with the slit, we had this psi function of the electron, right? And after the slit, we have this composition like C1 with psi function, the state function K1, let's denote it by this. So this is the state of electron going to this direction after this screen. Then another plus C2, another state K2 vector plus C3 state K3 vector plus etc. So we can rewrite the same in this form that we already used to write when we discussed the linear algebra, right? So this is a sum of some coefficients Cn, and these vectors Kn vector, like this. So this is the superposition principle, right? We have to take into account, or we have to take into account all these possible states in the system, from K1, K2, basically all of them, and all these states make the superposition, and this superposition of all these capabilities, or all these vector states, represent the initial state of the electron. Very good. Let's discuss another example. Example 2. Example 2. Example 2. Something like more related to us. So let's call this two-level system. Two-level system. Usually we denoted by TLS. TLS, two-level system. aka qubit. So you probably heard many times about this qubits, what the qubit is. So the qubit basically a two-level quantum system. Like any two-level quantum system is a qubit, or can be considered as a qubit. So let's write this. Let's sketch this two-level system here. So this state 0, or ground state. This is state 1, or excited state. All right. We have some sort of excitation. It can be electron or photon. And when we excite the system, we basically jump from the ground state to the excited state, like this. And so using the principle of superposition, the general psi function, this state vector is given by this expression, right? So it will be some psi c sub 0 vector 0 plus c sub 1 vector 1. And this vector 0 and 1, we already introduced them in the previous discussion. So it was 1 0 vector, right? And vector 1 is vector 0 0 1. Do you have any questions before we proceed to the second postulate?
No, Professor.
Very good. So the second postulate number 2, also known as Born rule. Born rule. Born is the name of a scientist, Max Born, very famous person, who basically introduced this concept, and for this concept he got the Nobel Prize. So the coefficients, these coefficients C in this series, right, in this superposition series, they correspond to the probability of finding the quantum state in a particular, the quantum system in a particular state. For example, in this slit experiment here, for example, this C sub 1 gives the amplitude of the probability of finding the particle in the state 1. C sub 2 gives the probability of finding the particle in the state 2, etc. So let's write this down. Born rule. The coefficients C n, right, in the expansions are the probability amplitudes, of finding the quantum system where in the particular state, in the particular state, right? So for example, in our example of TLS, two-level system, we had this superposition in this form, C0, 0 plus C1, 1, right? So now we take the product of this by bra, for example, bra 0, and what we get C sub 0 equal to 0 psi, right? So this C sub 0, this product is the complex number, sorry for my handwriting, right? complex number. So complex number cannot represent a probability, because probability is always a number from 0 to 1. 0, like you never find this particular like quantum system in this state. 1, you will find this system with 100% certainty in this state. So, and in general, the probability always like a real number between 0 and 1. That's why to find the actual probability, we have to take this complex modulus squared of this coefficient C sub 0, which is this, right? So this is the probability in this particular case, this C sub 0 modulus squared, the probability of finding TLS in the state, in which state? In state 0. And the same way, for example, C1 modulus squared is the same like probability of finding the state in the state one, in the state one. And in this another example of the electron passing through a slit, electron and slit experiment or example. For example, some Ci modulus squared probability of detecting electron in the state Ki, right? Or in other words, detecting the electron that was scattered to the direction of Ki. So this Ki is a vector, wave vector, right? Wave vector contains information about the energy and direction. So for this story, it's important that the K vector gives you the direction. So since these coefficients C modulus squared, they give you the probability of finding a system in a particular state. That means that if I sum up all these probabilities, Cn squared, I will get what? I will get 1, because because the total probability of finding a system in any state, in any possible state, is 1. Right? So because the total probability of finding a system in any state is 1. Like finding electron scattered like to any of these directions, probability is 1. Finding the excitation either in either the state 0 or state 1 is also 1, etc. Do you have any questions?
No, Professor.
Very good. All right, so let's jump to the postulate number 3. Postulate number 3. So this postulate is about observables. So we already mentioned that in quantum mechanics, basically, I mean, in physics in general, the observables are real valued numbers, right? And basically, because everything that we measure in a lab, for example, always real valued something, like a current, like a position of a particle, energy, all these things are real valued. And for this reason, the observables in quantum mechanics are represented by Hermitian operators, because Hermitian operators have real valued eigenvalues. So let me write this down. So physical observables observables are represented by Hermitian operators. This means that the classical quantities like radius vector, right? Position, coordinate, radius vector, momentum, p, also vector. What is like, for example, energy, and others, electric field, strength, angular momentum, etc., etc. So, etc. So these classical quantities that we measure in a lab are promoted to Hermitian operators. Hermitian operators. For example, for the operator R, we get, or for the radius vector, classical radius vector, in quantum mechanics, we get the operator R vector. The classical momentum we promoted to the Hermitian operator, P operator. Very important point, energy. We promote this to the operator Hamiltonian operator. We denote it by H hat, etc., etc. So basically, this is the correspondence principle. We have some classical value that we measure in a lab. For example, position of a particle, momentum, energy, etc. And in quantum mechanics, we represent all these quantities by corresponding Hermitian operator. So next, the possible results of measurement of these Hermitian operators, basically the possible results of measurement of these quantities are eigenvalues of the Hermitian operators. So the possible results of measurement are the eigenvalues of the Hermitian operators. Let's highlight this point in red. So what it means? So you have a classical quantity. You write down the operator, Hermitian operator for this classical quantity. And the quantum mechanics states that the values that you can measure in your lab basically correspond to the eigenvalues of the operator. And you cannot, so in lab, you can measure only the eigenvalue of the operator that correspond to this quantity. You cannot you cannot find any other value but from the like among the eigenvalues of the operator. You cannot measure something else but the eigenvalues of the operator. For example, spin. It can be either spin up or spin down. These are two results of measurement, and these are the eigen values, basically, of the corresponding operator. And you can never, in this experiment, you can never measure something in between. It's always up, or either up or down. Okay. So, for example, let's again consider this TLS example. Let's write down the Hamiltonian of a TLS two-level system or qubit, where in what representation? So let's consider the state, I mean this TLS system in the energy representation. In energy representation. So let's draw this system. So this is state, oops. So this is state 0, this is state 1, right? And well, I have some sort of electron excitation that can go up and down between these states. And this first state gets the energies E sub 0. The second one is E sub 1, right? So energy E0, E1, they attributed to this quantum states. And the fact that I am in the energy representation, in energy representation, the corresponding matrix of the energy, which is Hamiltonian. Hamiltonian is the operator or a matrix that represent this classical quantity, this energy in quantum mechanics. So I can immediately write this Hamiltonian, usually we denote it by H with hat, as a matrix 2 by 2. And in this representation, in the energy representation, this matrix must be diagonal. So it will be E sub 1 here, 0 here, 0 here, E sub 2 here. That's it. So this is basically the Hamiltonian of a qubit in energy representation. Let's discuss another example. What's 1, 2? Okay. So let's consider so-called coordinate representation. Coordinate representation. So energy representation that we just discussed is very important for systems like qubits, systems where we don't like aim to consider, to describe the trajectories of particles etc., and interested only in the energy of these states. This is basically something that we are interested in quantum computing, for example. But there is another very important representation. It's called coordinate representation. So in this representation, we actually interested in trajectories of particles, interacting of particles, and etc. So in this coordinate representation, our let's denote r vector. This is radius vector, right? And let's find the operator of coordinate and momentum. Operators of coordinate and momentum. Coordinate and momentum. So here we start with eigen function of such a quantum system. So let's consider a particle in a free space. So basically a particle that travels through free space. Particle in a free space. Particle in a free space. So no interactions, no other particles, just particle in a free space. So the particle, such a particle, is described by a plane wave. So like the way we describe a photon, right? This a particle of a light, for example, that travels through free space as a plane wave. In the particle like a electron, proton, neutron, etc. They also can be in the free space. They also described by a plane wave, and this is so-called Brillouin theorem, you might say. So the particle, the particle in the free space is described by the, let me write this in red, the Broglie, like this, right? The Broglie wave function. The Broglie wave function. So this de Broglie wave function is can be written this way. So this is was denoted by k vector. We also denoted by simply like this, the cat with k vector without writing psi. So this is the same as this k, right? And this is equal to some normalization factor, which is amplitude times the exponential function of IKR. Plane wave. So this plane wave travels along or in direction of K. So, and this is the way we represent like plane wave of any current. And de Broglie, this French, I don't remember exactly, I'm not sure, scientist, he said that we can attribute any quantum system, a quantum particle, like electron, a wave. So our particle is not just a particle, but also a wave. And in different situations, it can behave as a particle or as a wave. For example, when we measure electron, we always measure electron as a whole, right? We never measure just a like half of electron, piece of electron. We always measure electron as whole. So this is like a particle, but at the same time, when the electron passes through a slit, like shown here, we get diffraction. So this is diffraction of electron. And after this screen with a slit, the electron can go to many different directions. And this is exactly what we mean by the wave nature of the electron or any particle. Okay. So in the coordinate representation, any I mean, in the coordinate representation, the corresponding operator, which is R vector hat, right? What it is, like the same way like we discussed here for the energy representation. In energy representation, the corresponding operator, which is Hamiltonian.
Dr. Alex,
Yes.
I have a question related to this last equation
Uh-huh.
or the wave function that, like this equation tells about the state of a particle, right? Where it is.
Yes.
And then what is this ket of K? The second,
Yeah.
where you wrote the equivalent to ket of K.
By this, I mean that this is the state of electron in the state K. Basically, the electron that travels in direction of K vector K. So this K vector is different. I can write the same like K1 vector, which is like A E K1 R. Another vector would be K2, which is A E K2 R. K3, which is A E I K3 R, etc. And the total state of my electron will be the general state vector, like superposition of all these vectors, like C. Let's write this step by step. C1 vector K1 plus C2 vector K2 plus etc. So it's equal to the sum Cn Kn vector. This is what I mean by this vector.
Thank you.
Yeah, so this is exactly what we discussed in this slit experiment. So this psi vector, so this psi state is a general state of an electron. And this double slit, or not double slit, the let's say slit experiment or diffraction experiment allows us to reveal all these states that the electron can occupy, right? And the total state is the superposition of all possibilities in this experiment. This is what it says. So the Broglie wave function itself can be imagined as a plane wave that goes through the free space, etc. And this is just like a way how to think about this quantum particle. But the point is that this is just a one term in this superposition. And the actual state of an electron is the total, is the sum of all possibilities. Sometimes the electron can be prepared in a particular state, for example, K2. That means that the electron propagates in some direction K2. But in general, we don't know in what direction the electron propagates because of the diffraction, etc. For example, if you have a electron, how does it, the electron gun, right? It creates electrons one by one, but you have some distribution of the velocities of these electrons, so it can go to different directions. So, and before you measure the velocity of your electron, you cannot say in which particular state your electron is. And before you did this experiment, you have to assume that your electron is in all these states all together, like simultaneously. So is it clear enough?
Yes, Professor.
Yes, it is clear.
Yeah, so this quantum mechanics, it needs some time to like practice and get used to all this concepts. So, and after you like did some practice and read some books and etc., you at some point used to all these things, and it became like crystal clear to you. So it needs some practice and time. Well, so let me continue. So for example, here in this example one, when we discuss the system in the energy representation, the energy operator has only diagonal elements, right? Because for example, when I solve this equation for the eigenstates and eigenvalues, right, I will get this corresponding energy states, either 0 or 1, if I am in the energy state. In the second case, in the coordinates, in the coordinate representation, I have basically the same. So in the coordinate representation, the operator of a radius vector, operator of the coordinate, is simply the coordinate itself. So let's write this down. So operator of radius vector coordinate in the coordinate representation. Is simply what? Is simply the coordinate itself. So this is my radius vector operator, and this operator is equal to the radius vector itself. At the same time, for example, the operator of the coordinate x, operator is nothing but the coordinate itself. The operator or y is nothing but the y coordinate. Z, the same z. Because we are in the coordinate representation. But what about the momentum? So let's find the let's find the momentum operator in the coordinate representation. So by the way, if you would consider the system in the momentum representation, then in this representation, the momentum would be just the momentum itself, right? So, and the important point here to basically to understand is that any quantum system, generic quantum system, can be described in any representation. It can be energy representation, coordinate representation, momentum representation, and these representations are basically equivalent. The answer we get is like completely the same. So basically, what we derive, what we obtain in coordinate representation, energy representation, etc., is exactly the same what we measure in experiment. The results are the same. These representations just the way we describe the system. Just the way we describe the system. So now we are in the coordinate representation, and as we say this, in the coordinate representation, the coordinate operator is simply the coordinate. But what about the momentum? So, so in order to find the operator of the momentum, we have to solve the equation for the eigenstate and eigenvalues of this operator, right? So we basically take this operator, act on a general psi function in this coordinate representation, and the solution must be this eigenvalue times eigenstate, right? So in this case, this is the operator, operator P, and this is eigenvalue, this is eigenstate. So now we have to solve this for the de Broglie wave equation. Because this is our postulate that de Broglie wave equation is the eigenstate of the momentum operator. So let me recall that psi vector de Broglie is some normalization constant times e to the power of I k r. I k r. So now let's plug in this to this equation for the eigenstate and eigenvalues. What we get? We get this operator momentum, then A, which is constant, then exponential function EKR, and it's equal to the momentum eigenvalue, basically the value that we can measure in the lab, constant EKR. KR. So from here we see that we cancel down this constant A, and now we see that the operation of this operator, momentum operator, on a de Broglie wavelengths must give me the basically the eigenstate of this of the momentum. And yeah, by the way, the momentum and the wave vector k, they actually connected through the Planck's constant. So this is so-called Planck's formula. This is something also we know from the experiment. So this is momentum. This is a wave vector, and h bar, which is equal to h over 2 pi. H is the Planck's constant. Planck's constant. Planck's constant. Something like a constant that Planck introduced when he tried to explain the laws of the basically thermal radiation, black body radiation formula, famous formula by Planck, was derived using this Planck's constant, assuming that the radiation is emitted by portions, also known as quanta. That's why this name, right? Quantum mechanics, because something behaves like by portions. And the funny story behind this Planck's constant, that Planck actually didn't believe in that his formula that contains this Planck's constant is only possible way to describe the thermal radiation, and he dedicated like 20 years of his life to find another way to describe thermal radiation without this quantum theory, quantum mechanics. And he basically failed. So he didn't find a way to describe, he didn't find a way to avoid using quantum mechanics. Yeah, so basically Planck didn't believe in quantum mechanics. And Einstein, by the way, also didn't believe in some of these postulates of quantum mechanics that we already consider as very well established. Let's say this way. Yeah. So what kind of equation we come to? So we get this equation pi, this oops, sorry. P momentum operator e to the power of I k r is equal to momentum vector, not operator, a vector, e to the power of I k r. So now let me write down the result, and then I will show you that this is actually a correct result for the operator of momentum. So the operator of momentum is equal to minus I h bar, Planck's constant, times times this operator from the vector vector analysis. let's call this x hat. This is unitary vector in the direction x times d dx plus unitary direction y d dy plus unitary direction z d dz. And you also you probably know, like some of you who attended my lectures on electrodynamics, you recognize this operator as this nabla operator. X d dx plus y d dy plus z d dz, and x hat, y hat, z hat are unit vectors. So here in this coordinate representation, we talk about like our usual space, coordinate space, right? We introduce this x, y, and z lab coordinate system, x, y, and z. And this x hat is simply this vector, x hat. This is y hat. This is z hat. Okay. So using this nabla operator, we can write this formula in a simpler way, simple notation. This operator, momentum operator, is equal to minus I h bar nabla. And for example, for the operator of momentum x, what we will get? We will get minus I h bar d over dx. Py operator will be minus I h d over dy, and pz operator is minus I h d dz. So let's check that this formula is actually correct. So let's use this formula and plug in to basically to this equation for eigenstates and eigenvalues, right? So let me rewrite. So let me maybe copy this and put it down here. Okay, so now I plug in this operator y to this formula, right? What I get? I get minus I h bar nabla, then e to the power of I k r is equal to momentum e to the power of I k r. So now we have to take this nabla of e. So this, let me change my color maybe to the green one. So nabla of EKR. So when I take this nabla is simply the sum of the partial derivatives by coordinate, right? And this is nothing but taking the let's say derivative by r from this exponential function, okay, r. So when I take the so when I do that, I take the derivative of this exponential function, and of course the result is the exponential function itself, as you very well know, and then the product, and then times the derivative of the exponent, right, of the IKR. So it gives me IK vector. Right, so I plug in this here, and what I get minus IH, then IK e to the power of IKR equals to momentum e to the power of IKR. So at this point, I can cancel this exponential exponential functions. I times I gives me minus, minus gives me times minus gives me plus. So I get what? I get h bar k equals to momentum. So momentum is equal to hk, which is the classical definition for the momentum of the particle, what we discussed just here, talking about the Planck's formula. So this means that this operator is, gives the correct answer that is in agreement with the classical definition of a momentum. So let's discuss another example. So that was example 2. Now example 3. Example 3. Hamiltonian in the coordinate representation. Hamiltonian in the coordinate, the coordinate representation. So we already discussed the Hamiltonian, but in the energy representation, and we say that Hamiltonian in the energy representation is described by diagonal matrix with the energies of the every single state, right? E1, E2, and in a general case, if we have a system with more than 2 states, our Hamiltonian, let's denote this energy representation by this E index. This Hamiltonian in the energy representation will be something E sub 0, 0, 0, blah, 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 0, E1, 0, blah, 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 0, 0, E2, blah, blah, etc. So this will be a diagonal matrix with all diagonal elements that correspond to the eigen values of the Hamiltonian. But what about Hermitian representation? What about the coordinate representation? In coordinate representation. In the coordinate representation, we have to assign the radius vector operator to all of our particles in the system, and momentum operator to all the particles in our system. And in this coordinate representation, the Hamiltonian will be the sum. So the Hamiltonian is the operator that corresponds to a energy in a classical system. Energy of a classical system consists of two parts, as you remember from the from school physics, right? The kinetic energy and the potential energy. And in quantum mechanics, this kinetic energy is represented by the operator of kinetic energy, and it depends on momentum, and the operator of potential energy, which is another operator. It depends on coordinate in a system and in general of time. So classical kinetic energy, there is a formula for it. It is momentum squared over 2m, right? And this and this potential energy can be like, I mean, for different systems, for different types of interactions, this potential energy is like different. So in quantum mechanics, we substitute this classical kinetic energy with the operator, and this operator gets the square of momentum operator here over 2m. M is the mass of the particle, let's say. If you're talking about one single particle, then m is the mass of one single particle. So now we can find the square of this operator momentum. What is it? It is simply the momentum operator squared. So let's just take the square. So square of -1 is 1. I squared is -1. So I write minus, then minus h bar squared. And then this nabla operator squared. So the nabla operator squared is what? Is Laplacian operator, which is equal to d2 over dx squared plus d2 over dy squared plus d2 over dz squared. You can simply get this formula from the definition of the nabla operator. So this is the nabla operator. You simply take the inner product, and assuming that, or recalling that the that these unit vectors x, y, and z, if you take the product of x and x, it gives you 1, but x times y gives you 0. So after all these calculations, you will get this fact that the square of nabla operator is the Laplacian. So this equals to actually, let's write this way. So the operator squared momentum is equal to minus h bar squared Laplacian. So the kinetic energy operator is minus h bar squared over 2m and Laplacian. And finally, we find this Hamiltonian in the coordinate representation, which is minus h bar squared over 2m Laplacian plus this operator for the potential energy of in the system. So now, at this point, I already feel that probably too much information for today, right? So maybe we just stop at this point, and I will proceed next week with the rest of the formulation of quantum theory. So basically, we have other other two postulates and a couple of examples. So we will analyze this story next time, and also I will try to come up with some practice problems for you to practice a little all this. At this point, I mentioned that this, for example, this part, this Hamiltonian in the coordinate space, we will not need this for the rest of the course. The reason why I bring this to the analysis, to the story here, is to basically demonstrate how all what we are doing is connected to the quantum mechanics that you learn in the introduction to the physics, basics of physics, in your bachelor studies, right? You're already supposed to have the like introductory classes to quantum mechanics, etc. And you, I'm sure you discussed this Hamiltonian in this form, etc. And my goal here is to explain how all this connects to the more general quantum theory. So let me maybe summarize what we discussed today, just briefly. So so about this basics of quantum mechanics, first we say that a quantum system quantum system is a system that is in a quantum state. This quantum state is represented by a psi vector. This psi vector is a vector in a Hilbert space. This is some mathematical abstraction that we use to describe the reality. The psi vector, of course, doesn't exist in reality. This is just a way how we describe a system that is beyond of our intuition, let's say this way, because like we live a classical world, we interact with objects, with this classical world, and we have some intuition about it, and we developed classical mechanics based on coordinates, momentum, angular momentum, energy, all these things that well describe the state of a classical system. But apparently, quantum system is something very different. For example, an electron doesn't have the trajectory. it doesn't get the momentum and coordinate defined in the same time, and and the electron behaves as a wave in some particular cases, experiments. So definitely this is all beyond our intuition. And in order to build a theory based on the things that we used to, coordinates, momentum, energy, etc., to describe a quantum system, we introduce this concept of psi vector in a Hilbert space. Then we say that before we measure our quantum system, like in a particular state, we have to take into account that the system, like we have to consider the system in all possible states all the same time. And this is so-called the superposition principle. Superposition of all possible states represents the psi vector, right? Then we say that the quantum, the things that we measure in the lab are represented by Hermitian operators. And we recall two important properties of Hermitian operator. First one is that the Hermitian operator has real valued eigenvalues. And another property is that the Hermitian operator, the eigenvectors of a Hermitian operator represents a basis. We discussed this in the very beginning of this course, somewhere here, right, like in the beginning of the second lecture. The main properties of Hermitian operators: eigenvalues are real, eigenvectors of a Hermitian operator represent a basis. So this point is that we can use the eigenvectors of a Hermitian operator as a basis to describe our quantum system. We can use eigenbasis of energy operator or Hamiltonian, and it will be energy representation. For the same system, we can go to the coordinate representation, which is eigenvectors of a coordinate operator. And it will be a system in the coordinate representation. For the same system, we can jump to momentum representation and describe the system in momentum representation. And basically, how we choose the representation, basically, we just judge upon what representation simplifies the description. For example, this qubit in a quantum computing is a very, like, pretty complex system. It is a system of conductors, system of inductors, superconductors, etc. So it's kind of complicated system. And the description of this system in the coordinate space, the coordinate representation, would require us to describe all the positions of the particles in the system, and this is obviously not possible to do. You cannot do so. But if you describe the system in the energy representation, then it's very easy. So your complex system can be in either ground state or excited state. That's it. So the operator of this complex system will be just this matrix 2 by 2 with 2 energies. And yeah, and then we talk about the Hamiltonian in the energy representation and Hamiltonian in the coordinate representation. So, okay, so next time we will practice a little and continue this description. So let me stop the recording and we can discuss if you have any questions.